Okay, so you should have all had enough time to work on the warm-up problem, identify the parent function, and describe any transformations that we've put on it. So let's talk about that. And we said the parent function was at its heart the simplest version of whatever we're graphing. You know, for example, every function that we express as mx plus b or ax plus b, however you want to think of that, is some transformation of the function f of x equals x. So if we want to identify the parent function here, we want to try and break this down to its simplest idea and then connect to the transformations that we're doing. So what do you think? What's the smallest function that we're working with here? And smallest not necessarily meaning lowest in value, but of the parent functions, which chunk seems to be the one that's driving the bus here? Okay, the square makes me think that this is a quadratic. I'm going to change the name. I'm not going to use f of x again. Okay. And now the question is, how do we transform it? What's going on? How do we get from G to F? Okay, and actually let's name this a quadratic. So, for our transformations, let's respect order of operations. Let's go with inside parentheses first. This -1, we're shifting to the 1. And remember, we talked about how when we're doing our x transformations, the transformations behave kind of the opposite of the way we expect. So this -1, we expect it to be a left transformation, a left shift, but it's actually a right shift. Okay. Now what? What's the next transformation we have? Well, we have this 3, if we're still respecting order of operations. And remember that multiplication by a constant always tells us that we're scaling. Okay, we're either stretching it out or compressing it down. Here, the absolute value is greater than 1, so we're stretching it. Okay, and then finally our +2, that tells us that we're grabbing the entire graph and shifting it up 2. So that's a vertical shift up 2. Okay, so not bad. This whole warm-up took us like 5 minutes. Questions on anything we've done here? All right, so let's move on. Today, we're going to talk about combining functions. We are going to use our basic arithmetic operations, addition, subtraction, multiplication, and division, to combine 2 functions into 1. And by extension, we can use that to combine 3 or more functions into one single function. We'll talk about how these combinations affect the domain of our functions. And then we'll find another combination process called composition. Composition sounds intimidating, but it's just using one function as the input for another. We'll explore how the domains are connected there. And then we'll do some evaluation of these combined and composed functions. So questions before we get started? All right. So when we're using our arithmetic operations to combine functions, we're introducing new function notation. So if I have this notation, f plus g of x, that's how we read this. It's still, the new function is f plus g. And our input variable, or our independent variable, is still x. What this means is probably what a lot of you are assuming it's going to mean. But you might also be thinking there's no way it can be that easy. Let's just take f of x and add g of x. And this actually works for any functions f of x and g of x. As long as I have those two functions, f plus g of x is just adding the two functions together. So from there, you might expect that f minus g of x behaves the same way. And it does. And similarly, multiplying our two functions together works exactly the way you expect it to. And dividing two functions works the way you expect it to, and some of you are already ahead of me. We've said before that whenever we're doing a division, there's one thing we always need to look out for. Not even something that needs to stay in the back of our mind, something that needs to stay right up front. And that is, we cannot divide by 0. So, I want you to get some practice with this. So, let's say on your notes, you have two functions. And I'm going to change colors here so we can track where things are going. So if I have f of x is 4x minus 6, and g of x is 2x squared minus 3x. I want you to find these four combinations of functions and fully simplify them. So I'll give you a few moments to do that. Work with your partner and come up with your results. Remember, the instructions are find and fully simplify. We've talked a lot about what fully simplified means. Okay, now I'd give them about 5-10 minutes to work on this. So let's talk then about what's going on here. First, If I want to do f plus g of x, well, that's just going to be 4x minus 6. Actually, let's follow our notes up here. We have f of x plus g of x. And you don't need to show all this on your work. But remember, show me enough work so I understand what you're thinking about. Show enough work so that someone like you, but who's not in this class, understands what you're trying to say. So I've got here, f of x is 4x minus 6. And g of x is 2x squared minus 3x. So now if I want to combine these to fully simplify them, okay, I'm looking at just combining like terms. I only have the 1x squared term. But I've got 4x plus negative 3x. And I've only got the one constant of plus the negative 6. And we've talked about putting the negatives inside parentheses. That way we don't have to worry about getting lost in all the sign changes until we absolutely have to worry about them. So now, combining like terms, 4x plus negative 3x is just x, and plus negative 6 is minus 6. So let's skip ahead. In class, we'd go over all these, at least go over the solutions. And if anyone had questions, we'd go back and talk about them. Let's look at the division problem. Combining these using division. So this is going to be f of x over g of x okay, do our substitutions in. Four x minus 6 over 2x squared minus 3x. Now we want to fully simplify this. Okay, so let's look and see what we can get rid of. 4x minus 6, I can factor a 2 out of the numerator. Two x squared minus 3x, I can factor an x out of the denominator. Okay, these two factors divide to 1. So we're just left with 2 over x. And we know we can't divide by 0. There's one other excluded value in here. Because remember, we're not just looking at excluded values from our fully simplified form. We need to look at excluded values from our original form too. So we need every value where g of x equals 0. We need to exclude all of those. And it turns out that when we I'm going to use the bad word, canceled 2x minus 3, we can't have that factor equal 0 either. So x can't be 3/2. All right, so questions with any of these examples? All right. So let's then talk about working with the domain of these functions. What does it look like? What does the domain of f plus g of x look like? Well, every value, or every real number for x that makes both sides of the equation make sense as mathematical entities is going to be included in our domain. And it has to be both sides. If it doesn't make sense for either side, we can't use it in our domain. So our combined function can't be any less restrictive than, or can't have a domain that's any less restrictive than the domains of the functions we used to combine them. So for all three of these first ones, the addition, subtraction, and multiplication, spell multiplication, let's abbreviate multiplication correctly. The domain is the set of all real x values. Okay, and remember we talked about some of the weird notation that you might see if you get talking about set theory. So this would be the set of all x's in the reals. Where f of x, g of x are defined and the combined function is also defined. So, one thing we can do to talk about the domain here is we can first identify the domain of f. Okay? And then from there, remove or exclude any values in the domain that are not also part of the domain of G. And then from there, remove any further values or exclude any values from the domain that also make our combined function undefined or non-existent. And so here we have our set of x as an element of the reals where, I'm trying to think of a way that we can talk about this without getting all kinds of weird set notation. And I'm honestly not thinking of one. We could say x is in the intersection of the domain of f, domain of g, and the domain of whatever operation we're using to combine them. But I wouldn't worry about this. I introduced it, so I wanted to finish it. Okay, with the division, we need to be a little more restrictive. Any value that in the domain of f starts out okay. For division, start with the domain of f. Exclude any values not in the domain of G. And also exclude any x where g of x equals 0. So we start with the domain of x, and then we start taking out, we start excluding additional things. So basically what this means is our individual parts need to be defined, and our end result has to be defined as well. So start with one domain and then exclude values as we go. All right? Now in class we'd move on to composition of functions, but the demonstration is only 20 minutes, so we're done here.